Welcome to the ePathshala lecture series on computer science for postgraduate students. We are in the 17th module of computer graphics. So, we have learned in the previous module about 3D viewing, which is an important topic, where we have learned projections, where we have talked about a parallel projection, we have talked about perspective projection, and we have derived some the matrices that correspond to each of these projections. So, let us quickly go into the next module, which talks about where we will discuss about visible surface detection, which is an important aspect of computer graphics. Okay, here in this module we talk about we will be fully thinking about the 3D world. So, we imagine that all the objects are in the 3D world, are all placed in the 3D world, and then say given a vantage point, or assume that we are standing at one position and we are viewing the 3D world. So, we see some of the surfaces and we do not see some of the surfaces, we see some objects, we do not see some objects because of their arrangement in the 3D world, and not only due to that, one object that is bigger or maybe one object that might obscure the other object. So, there are possibilities that an object is hidden by another object. So, from a given viewing position, some objects are visible and some objects are not visible, and to be more specific, some surfaces are visible, some surfaces are not visible. So, what we will see in today's module is about visible surface detection, and in graphics terminology this is also called as backface removal or hidden surface removal or backface culling, and there are many names used in the literature. So, than to remove something that is a back face, what we will do here is we will consider a face that is visible from a given viewing position. So, what do we do? Let me repeat that again. What do we do in this is we select faces that are visible and we ignore faces that are not visible. So, that will be the discussion today. So, let us see what are the various, so these are the various the team members who are involved in this exercise. So, the objectives of this is to understand the need for visible surface detection in computer graphics applications, and we will look at the common classes detection methods of visible surface detection methods. So, some of the common techniques that are used for visible surface detection, and the keywords are image space, object space, visible surface detection, hidden surface removal. So, we can classify these visible surface detection algorithms into either object space or as image space, and we can combine the object space and image space and call them as mixed methods. So, we have three classes here, one is object space, the other one is image space, and the other thing is combining both we have a mixed method, a mixed set of methods. So, what is object space? So, object space says that we imagine that we are in the 3D world and we identify objects that are visible within the 3D world and which are obscured or which are hidden in the 3D world by other objects, and then we identify only those surfaces that are visible and label them as visible. So, we compare each object in the 3D world with respect to other object and determine what is the frontal face or what is the back face and how do we remove them. So, that is completely in the object space. Whereas, in the case of image space, what we will do is we will take a projection of the 3D world onto a 2D plane. So, that means what do we do is we assume that we are viewing from some position, and at the position where we are standing or we are viewing, we imagine a 2D rectangular plane, and we assume that the 3D world is projected onto the 2D plane, and we then try to see what should be the final value at each and every pixel position from the given viewing position. So, we check which face is to actually should be plotted on the 2D map or in a 2D plane. So, we look at the projection of the 3D world onto a 2D plane, which is all about the image space methods. So, the image space methods rely on this technique. So, mixed methods use a part of comparison in the object space, a part comparison in the image space. So, that is how these mixed methods work. So, we will see examples for object space and image space, as they are generally most popular, most common methods exist. And let us you can ask me one question, like say, why should we remove a surface that is not visible? Why should we remove back faces? So, the fundamental question is, why should we do this at all? The answer is, why should we include faces or surfaces in the from the viewing position, or whichever are visible from a given viewing position? Why should we include those faces or surfaces which are not visible from a given viewing position? When they are not visible, we do not have to apply, we do not have to manipulate the object surface at all. We do not need to manipulate that at all. So, we can save lot of resources, a lot of time, lot of computational capabilities, and the operations are much quicker. So, the essence is identify faces that are not visible, and we do not want them at all in the scene, and only take those faces that are visible and do whatever operations you want to do only on those visible faces. So, that is where we save lot of time, effort, and operational requirements and resources and so on. So, let us start with let us see the classification of the methods. As we saw in the previous slide, the visible surface detection methods are classified as either object space or image space or mixed methods. The classification goes like this: a simple backface detection method, the A buffer method, so we call it the accumulation buffer, the A buffer method, the BSP tree method, the binary space partitioning tree method, the octree method, or they are classified under object space methods. The other class of methods are depth buffer method, which is a famous example for image space method. A depth buffer, and in literature it is also popularly referred to as the Z buffer method. The scanline method and array casting is a technique used in the image space methods for visible surface detection. And finally, the mixed methods, they are depth sorting and area subdivision, are more complex methods. We will not focus on them in this session, but we will focus on at least one example for each of the object space and image space methods. Okay. So, fundamentally all these techniques, whether they are object space methods, image space methods, or mixed methods, they rely on two fundamental principles. They are sorting and coherence. So, sorting is to sort faces from as per their depths from a given viewing position. So, sort faces in the 3D world. Faces here is actually, face can be a surface or a face. So, a face is a plane which is a part of an object. You can consider, say, if you imagine a 3D cube, if you imagine a cube in a 3D world, one of the faces of the cube is actually what we mean by calling it as face, or you can also call it as a surface. Okay. So, sorting is like, say, how do we sort or how do we arrange these faces as per an order, in some order, and coherence is like take advantage of a kind of similarity or regularities within objects or within planes or within surfaces and within parts of a scene. Let us look at the very first method and for visible surface detection, which is the simple backface detection, which is an example, which is categorized under object space methods. As you can see in the slide there, from a given viewing direction, if a face is not visible, it is considered as backface. So, the important observation is, given a viewing direction. So, you can imagine a position in the 3D world, and from that viewing position, if something is not visible, we call it a backface. Sometimes the name backface culling is used, and if you look at the terminology in different books, you will also find that the word culling, it is called backface culling. Okay. So, as you can see the example there in the slide, a cube is given, and imagine your cube is oriented in such a way that you can see only the 3 faces of the cube. The remaining 3 faces or planes of the cube are not visible. So, do not include them at all in the picture, so that we can avoid a lot of processing and a lot of manipulation and time and so on. And the very first visible surface detection method is the backface detection, which is a category of object space methods. As you can see, there is in brackets it is given as OS. OS indicates object space method. So, we will take examples for object space method and later we will see examples for image space methods as well. So, the very first thing is the object space method. So, what does it say? It is the simplest most method. Imagine you are given a 3-dimensional viewing coordinate system. So, always where we are standing, from there you erect 3 mutually perpendicular directions and that forms your viewing coordinate system. Okay. So, imagine you can choose your right handed coordinate system, as you can imagine the 3 coordinates which are the right handed, which are the first 3 fingers of the right hand, where the negative z direction is always the viewing direction. So, imagine there are so many objects placed in the 3D world. As you can see in the example shown there, in the diagram shown there, there is a pyramid like object, and we can assume that a plane or a face or a surface of a 3D object can be, if you imagine that to be a plane, then we can assume an equation for the plane as Ax plus By plus Cz plus D is equal to 0 can be the equation of the plane. Okay. So, if you imagine a pyramid like thing, so there are 4 such and 5 faces for it, and we have the equation that defines a plane as Ax plus By plus Cz plus D is equal to 0, and a normal vector to the plane is nothing but the components of the equation. You can take the A, B and C, the coefficients, and they automatically are the normal vector components for the plane. So, a normal vector is very important attribute for a plane. A normal vector identifies the orientation of an object in the 3D world. So, the essence is that when your viewing direction and when the normal vector direction of a plane are aligned with each other or almost in the same direction, then we say that we are actually seeing the back side of it or the back face, we call it a back face. That means imagine you are sitting in a classroom, okay. What you see is actually what you are seeing is the inside face of a, so because assume normal vector is always an external outside and perpendicular to the plane that we consider. So, a normal vector is actually the direction of the normal vector, and if your viewing direction are aligned, so that means you are inside a classroom and you see actually the back side of the walls. Okay. So, that is how you can imagine. So, imagine that the room is closed or the classroom is actually fully closed, and imagine it is a closed box like shape, it is a cube like or cuboid like, and you have the normal vectors which are external and outward. So, the normal vector direction, and if you are inside, you are seeing the back side of it. So, that is how we can classify objects or faces as either front face or a back face. So, from the discussion given here, it is evident that it is given there as if where the direction is along, the viewing direction is along the normal vector direction to a face, we are seeing the back side of it. A point Pxy is an inside point, as you know, given a plane equation, an inside point is something that lies on the plane, okay. An outside point is away from the plane, okay. This inside and outside should be understood carefully. A point Pxy is an inside point if it satisfies the condition Ax plus By plus Cz plus D less than 0. If it is equal to 0, what we say, it is a point, it is the equation that defines the plane, and it is less than 0 is a point on the plane. You can also include P, X, Y and Z, you can have that Z coordinate in the point. So, when an inside point is along the line of sight to the surface, the polygon must be a back face. What is that? Observe that carefully. When an inside point is along the line of sight to the surface, the polygon must be a back face. Okay. So, if you can define the normal vector components as ABC, because the equation of the plane is Ax plus By plus Cz plus D is equal to 0. So, the normal vector components are obviously ABC, and the viewing vector, as we know, the viewing direction is along the negative z direction if you use the right handed coordinate system. So, along the negative z direction, x coordinate is 0, y coordinate is 0, and z coordinate is actually negative. So, Vz, if you take the V vector which is the viewing vector direction, the components are 0 0 Vz, where Vz is the z component of the viewing vector, which is in fact negative. Okay. So, when you take the dot product, so the polygon is a back face if the angle, if the dot product between the two vectors is greater than 0. So, when the dot product will be greater than 0, when the Vz is negative, we have to also consider that is because it is negative, V dot n is equal to Vz into C, as you can see, because the A into 0 dot product, it is simply dot product, A into 0 0, B into 0 0, then Vz into C is the dot product. So, that is what is left out of the dot product. This dot product has got Vz which is negative in fact. So, if C is negative, the dot product becomes positive. Vz is negative, if C is negative, the dot product becomes positive. So, V dot n is greater than 0. So, whenever C is less than or equal to 0, we can safely conclude that we are seeing the back side of a face, we can ignore the face. So, we can call that as back face. So, that is the important discussion in the very first and the simplest method for back face detection. The other back face detection method that is most popular in the visible surface detection methods is the Z buffer or the depth buffer method, which is categorized in the class of image space methods. So, in the previous example we have seen an example for the object space method. In this is an example for image space method. What is an image space method? Again, as I said in the beginning of this discussion, we take a projection of the 3D world onto a 2D plane, and there we check for each pixel what is the possible visible surface, so that we can color that pixel with the color of that surface okay, that we see. So, that is how we do it for all of the pixels, for all the pixels in the 2D plane. We take each pixel at a time, and we start with the first pixel, the corner, say the left corner pixel, top left corner pixel, and we try to sort the surfaces as per their depths, and then we will see which surface is the frontmost surface and give the pixel that color, the color of that surface. So, that is what we are going to do in the Z buffer or the depth buffer. So, depth, the Z itself is generally understood as depth. Okay. As you can see in the slide there, the object depth is measured from the viewing plane along the Z axis of viewing system. Each surface of a scene is processed separately one point at a time across the surface. So, we take one surface at a time. Okay. The method can be applied to both planar and non-planar polygon surfaces. Again, planar polygons is of interest to us. Non-planar polygons are like one of the vertices of the polygon are not aligned with the other vertices of the polygon, or not in the plane of the same as that of the other vertices. So, we can call that as a non-planar polygon. So, they are still polygons, but they are non-planar. Okay. Two buffers are used, one is the depth buffer and the other one is the refresh buffer. So, depth buffer is used to store depth values for each xy position as surfaces are processed. The important statement is given there for this Z buffer algorithm. Depth buffer stores depth values, and refresh buffer stores the intensity buffer stores the intensity values at a given xy position. So, as we process a frame. So, the Z buffer method is clearly given in this picture, as you can see the picture there. So, we are viewing from a viewing direction or from a viewing coordinate system along the negative Z direction. Always imagine this, keep in mind we are viewing the world along the negative Z direction. Okay. Now, what do we do is we have chosen a view plane which is a bigger rectangular plane, and we start with, we take one pixel position at a time on this rectangular view plane. We take every pixel position which is an xy position, Z is constant. So, that means we are taking only the xy. So, because if we imagine this view plane to be the xy plane of the viewing coordinate system, then the Z coordinate is obviously 0. So, the xy coordinates only make sense here for assuming that the view plane is some plane that is either z is equal to 0 plane or z is equal to some constant plane. As you can see, their surface S1, S2, S3, there can be n number of surfaces. Imagine we are viewing exactly along the perpendicular direction. Assume you are firing a perpendicular direction from a given pixel position. The direction is perpendicular to the view plane. So, imagine a view plane and the direction is perpendicular to the view plane. So, S1, S2, S3 and Sn can be n number of surfaces, and you can order them as per depths. Okay, the important point is you can order them as per depths. Okay. So, one surface may be obscuring the other, but initially you first order, and later what do we do is whichever surface or face is closest, is visible, is closest to the view plane is the color of that is to be taken for that pixel. So, the algorithm is as simple as initialize the buffers. We have got two buffers, one is the refresh buffer, the other one is the depth buffer. Refresh buffer is initialized to the background color, and depth buffer is initialized to a value 0. So, for each polygon, so take one surface at a time. So, one face or one surface at a time of an object. Okay, you can imagine many 3D objects in the 3D world, and take one polygonal face at a time and compute the depth value for the polygonal face. Again, imagine there can be planar polygons or there can be non-planar polygons as well. So, take one polygonal face at a time, compute the depth value z. How do we know at what depth the polygonal face is? Okay. It is also interesting that at every pixel position on the view plane, when you process the same polygon, that might be at different depths. So, it is also possible. Okay. So, z for every xy position may be different. Okay. If the face is exactly parallel to the view plane, okay, then the z for all the pixels of the face will be exactly the same. Okay. We do not have to really worry, but if the face is oriented like this and if the view plane is like this, then you have for every pixel position you have a different depth value. So, as for each polygon, do this processing, compute depth z for each xy position on the polygon. If z greater than depth x comma y, that is take each xy position and keep processing the entire thing. Okay. For every xy position, what you do is compute depths. Okay. If the depth is greater than the previous position, so default is 0, default depth is 0, and if it is greater, because we are in the negative z direction, the negative values that are larger is understood that they are backward. So, they are not in the front, they are in the back. So, the smaller the magnitude, the closer is the object or the face. So, as per depth we can keep comparing for every pixel position on the view plane, take a polygonal face, take one polygonal face at a time and start with the xy position, the first pixel position on the view plane, and fire a line into the 3D world and see where it hits the polygonal face, compute depth, and then keep doing this for all the faces and take the color. So, that is how we do it, and finally what color the pixel has is exactly the color of that face, that polygonal face that is closest from that position for that xy position. So, how do we know what is the depth of a polygonal face? Given a polygonal face with the equation ax plus by plus cz plus d is equal to 0, how do we compute depth? Depth is the z is the depth for a polygonal face. How do we compute z? Z is equal to minus ax minus by minus d by c, and we do not have to really do this for every what is called pixel position. Instead you can use coherence, instead you can use what is called similarity, that is for the next x position for the same face, the next x position on the view plane for the same polygonal face, you can easily compute, replace x with x plus 1 comma y. You consider a scan line, replace x with x plus 1 comma y, and wherever there is x, if you replace that with x plus 1, what happens is minus a times x plus 1 minus by minus d by c, and you can expand that inside, and minus Ax minus A minus By minus d by c. So, already minus Ax minus By minus d by c is the previous depth z at x comma y. So, we can conveniently replace that with x comma y. So, we have recursive equations here. The depth at the next x position is given by the previous x position minus a by c, the depth at the previous x position minus a by c. So, we have recursive equations here which are very faster when in implementation in a program. So, imagining we have got one scan line. So, we go row wise, one row at a time. So, we fix a y and we keep doing this across the y, and then take the next y on the view plane and do the same thing, and we keep doing this for all the pixels in the view plane. Okay. So, we can also do this recursively along an edge of a polygonal face by taking y minus 1, and we can easily do this using because as we know the next x dashed is equal to x minus 1 by m, you do not have to really compute, you can use again recursive equations. If you do a computation on the previous step, you can use the computation in the subsequent step using recursion. As given there, the next x position is x dashed is equal to x minus 1 by m minus that is substitute in place of x minus 1 by m in the previous equation for z, and what we get is minus Ax minus 1 by m minus b into y minus 1 minus d by c, which is zx comma y plus b by c. As we know, m is negative for this for the edge that is like this. So, m is negative, so the equation is x minus 1 by m. So, that this is how we look at the depth buffer method, a very important thing in the visible surface detection methods. It requires two buffers, the depth buffer and the refresh buffer. It deals with only opaque surfaces. So, there are some drawbacks of it obviously. It takes up only one phase at a time for processing. It does not take multiple phases at a time. That is one drawback, a major drawback. So, but the advantage, as you can see, it is simpler, it is easy to understand, no sorting of surface is required, polygons may be processed in any order, it is easy to implement. The next important method which is very popular in the visible surface detection methods is the scanline method. Okay, we have seen the simple backface detection method, which is an example of object space methods. We have seen one example for image space methods, which is the z buffer or the depth buffer method. Another interesting example is the one of the image space methods, an example for image space methods is the scanline method. Okay. So, this scanline method it works like it assumes a scanline across a polygonal face, and the advantage over the depth buffer method is that we can process a number of polygonal faces simultaneously. So, we do not have to take each polygonal face. So, there can be too many polygonal faces in a scene. So, we cannot afford to take each and every face at a time, and sometimes there can be opaque faces, there can be transparent faces, there can be any type of faces. So, we need to process multiple faces at a time. So, this scanline method is advantageous as we can take care of multiple faces and faces that overlap on each other as well. So, there is an extension this algorithm can be used for polygons that are intersecting across a scanline. Okay. Process from left to right and depth calculations for each overlapping surface. So, we can have n number of overlapping surfaces like this, and we can process all of them at the same time. That is the advantage of this method. The intensity of the nearest position is entered into the refresh buffer. So, let us see how does this work. So, as you can see in the picture there, we have two surfaces, we can call them either a face or surface. So, imagine they are all planar. So, both of them are planar. The first surface is identified as S1, the other surface is identified as S2, and where S1 and S2, a part of S1 is overlapping on S2, that means there is a partial overlap between the two faces. Now, S1 is determined by A, B, C, D, and S2 is determined by E, F, G, is identified by the 4 vertices E, F, G, H. Okay. Now, the first scan line, as you can see, it is intersecting the edge AB of S1 and edge EH of S2 and also edge BC of S1 and edge FG of S2. So, it is intersecting 4 edges of these 2 surfaces of these 2 faces. So, but if you look at scan line 2 and 3, the number of intersections that it does is still 4, but the difference between scan line 1 and 2 is that, as you can see, scan line 2 and 3 is there is no difference here. As you can see, scan line 2 intersects AD, scan line 2 intersects the EH, as the next intersection point is on the EH edge. The next intersection point for the scan line 2 is on the BC edge, and the next intersection point is on the FG edge. So, this the intersections are exactly the same for scan line 3 as well. So, 2 and 3 we can use the principle of coherence. Okay, we can use the principle of coherence. So, whatever we do for 2 can be exactly copied for 3, and we can simply do not have to bother about the rest of the computation. So, we can exactly copy the same set of operations that we did on 2 for 3, but 1 is different from the 2 and 3, because 1 intersects AB, a different edge, then BC, then EH, then FG. So, what we do is we note these intersections, and then between one edge to the other edge we take the color of the pixel, color of the surface, whichever is being intersected, say S1. Between AB and BC, S1 is to be selected for scan line 1. Between EH and FG, for scan line 1, select surface S2. Between the edges BC and EH, there is no intersection, or there is it is like an open space. So, we do not have to bother about it. So, do not take anything there and beyond. So, that is how we try to select each scan line, and we prepare an active list here. What is an active list? Active list is the edges across the current scan line. So, whatever edges that the scan line touches, and they are also sorted in the order of increasing x. As the scan line intersects each edge, see the x order. So, put them in ascending order, that is increasing order. Flag each surface and indicate whether it is on or outside of the surface. So, as I said earlier, it is S1 as long as we are between the 2 edges of a scan line of a surface, the surface should be on. When we are outside of the surface, it should be off. The surface should be either on or off. On or off here means we are taking the color of that pixel, the surface pixel, or we are not taking the color of it, that is it. It is on or off means that. So, at the leftmost boundary of the surface, the flag is turned on. At the rightmost boundary of the surface, the flag is turned off. So, that this is an interesting method. Here no depth calculations are really necessary, and for the active list 1, for the scan line 1, but for the scan line 2 and 3 we may have to compute also the depths. Okay. Scan line 1 is to be treated differently from scan lines 2 and 3. For scan line 1, no depth calculations are required. Intensity of either S1 is on or S2 is on, as you can see for the discussion in the given in the slide. For 2 and 3, we need to also look for what is the combined color. So, for scan lines 2 and 3, there is an overlap. So, they are going across an overlap region. The overlapping region is between EH, the overlapping region is between EH and the BC edges. So, for the overlapping part or overlapping region for the scan line 2, we need to combine the colors of both surfaces S1 and S2, and then we can give a combined color there. So, that is the interesting point. If S1 is prior, okay, we can, if they are opaque, we can take the color of the surface that is overlapping the other. So, the color of the surface that is to the front. If it is a transparent surface, what we can do is we can take the combined effect of both, and we can take the common color there. So, it is a very efficient algorithm, as we can process multiple surfaces at a time. Only when overlapping is there we need to calculate depths, otherwise we do not have to. It takes advantage of coherence, and the advantage and disadvantage does not work for surfaces that cut through or cyclically overlap each other. Takes advantage of coherence, many overlapping surfaces can be processed. So, here we have learnt in this module how visible surface detections are classified and we have seen examples for each of them. One is for object space method we have seen, and we have seen 2 examples for image space method. So, you will be able to you can explore more on our books and other literature. Thank you.